All right. So what we're going to look at now, okay? Let's just brief overview of the mean value theorem, okay? The mean value theorem essentially says this. So this is 4.2 mean value theorem. The mean value theorem says that for any interval, and actually any open interval, okay, any open interval a to b, there exists a c belonging to a to b, okay, such that, all right, f of, excuse me, such that f prime of c is equal to f of b minus f of a over b minus a. Provided that, okay, we have to have these things be true. Provided that, okay, f is differentiable on a to b, so the open interval a to b. 2, f is continuous on the closed interval a to b. Okay, so provided that we have those two things, then what we have is we actually have that we know that this is going to be true. Make sure that I've got it. Okay. Yep. Open interval for a to b, closed interval a to b, f is continuous. So if we've got those two things, then we have this. Now this thing here, you may notice, okay, f of b minus f of a divided by b minus a is the slope of the line, okay, is the slope of the line from b to a, right? All right, so it's the slope of the line from b to a, and if you remember, and this is a little while back, if what you want to remember is, excuse me, that this is also the average, okay, value, okay, the average value for the slopes of the tangent lines, okay, between b and a. So basically, that's kind of why it's called the mean value theorem. It's the average values of all the slopes from b to a, okay? So like, you know, essentially what we're going to get this picture that looks, excuse me, sorry about that. We'll get this picture, looks something like this, okay? And so like, let's say, for example, here's A, here's B, and I have a line that goes from A to B. So there's A to B, okay? And that's the average value, okay? The slope of this line equals f of B minus f of A over B minus A. And so we imagine if we have a line, right, that's continuous and differentiable, somewhere along this line, and maybe even more than one time, but somewhere along this line, we'll get a tangent line, say, for example, right about here, okay? We'll get a tangent line that has a slope exactly the same as the slope of the line between B and A. Okay, and that's it. That's the mean value theorem. That's the basic idea of the mean value theorem. So what we want to do is we're going to use this in order to show, right, that we're going to have, we'll take a look at what the requirements are. Give you a second to write this, okay? So we'll go back, right? So what we want to show, right, is that there exists a C on A to B such that f prime of C is going to equal this, equals that derivative. And then our requirements, so we first need to show this. So take a look at those. One, f is differentiable on A to B, and then two, f is continuous on A to B, on the closed interval A to B. So those are the two things that we're going to have to prove in order to use the mean value theorem, okay? So at each step along the way, we're going to be like, okay, so I want to use the mean value theorem. So first I need to show that f is differentiable. And then secondly, I need to show that f is continuous, okay? And so you're like, okay, how do I show something's continuous, right? How do I show something's differentiable, all right? That's kind of the idea. And then once we do that, then this actual result here, the result of the mean value theorem comes out. Then we know that there is a C belonging to A to B such that f prime of C equals that, that slope. Any questions?
Yeah, I did have a question, Professor.
Yeah, what's up?
If you actually, can you go back to the graph? I just wanted to check
Sure.
something.
Yeah.
So where you're doing the slope for the point near the, well, I guess right there would be the maximum. That's not at the maximum, right?
It actually, no, the
Because
maximum
wouldn't
will
that
have a
be
slope of
0?
0. Yeah, that's right.
Okay.
And that's
'Cause
Rolle's theorem.
okay. So this is closer to like the left, right? So it's not exactly at the max. That's why the slope is the same as the other one.
That's right. Well, and
Okay.
it doesn't really matter whether or not it's at that one or anywhere else. It doesn't really matter where it's at. Okay. It just happens that in my picture, that's where it's going to be located because that's where the tangent line has a slope kind of similar to b minus a. You can
Okay,
actually see there's one down here too. Oh, sorry. But there's another one down here.
yeah.
Yeah. You see that one too?
Okay, so it's not at the critical point. It's like near the critical point.
That's right. And if we look at Rolle's theorem, which is the introduction theorem that we had from this, Rolle's theorem actually says that if we have, and they're equal to each other, so let me kind of, I'll show a Rolle's theorem one. Okay. So for Rolle's theorem, right, what we have is A equals B. So Rolle's theorem is a special case of the mean value theorem. We'll have A equals B, and then this says that there exists, right? There exists a C, a C such that, C belonging to A to B, such that f prime of C equals 0, okay? Right? And so for Rolle's theorem, what we're getting is we're getting something that looks like this. Okay, so now A equals B. So like we imagine we've got A equals B, right? So we've got to have something that looks kind of like that. By the way, Rolle's theorem also requires differentiability and continuity, okay? And then what you see here is, so right here, we have to hit a maximum according to Rolle's theorem, right? So in that case, okay, right, f prime of C equals 0 at that point. But you can also see, if you look here, okay, take a look, right? Since A equals B, f of B minus f of A equals, no, not since f of A equals f of B. It's not, okay. Giving me a side note, f of A equals f of B in Rolle's theorem. That's what we need, excuse me. Since f of B minus f of A, since f of A equals f of B, f of B minus f of A over B minus A, excuse me, is going to equal 0 minus 0 over B minus A. So it's going to end up equaling 0. So it's also the same kind of like idea as the mean value theorem. It's just in this case, the slope between A and B is 0. All right. let me kind of reiterate that because I was a little all over the place. So in Rolle's theorem, what we had was f of A equals f of B. So what we know is then that there exists a C belonging to A to B, okay, such that f prime of C equals 0. All right? If we, kind of prove each step first, one at a time. So what that means is that somewhere we're going to have either a max or a min. We're going to have some kind of critical number, right? Like f prime of C equals 0, like in our case. And the reason why that is the case is because, right, since f of A equals f of B, that top part's going to equal 0. So the slope of the line between A and B is just simply 0. So it's the mean value theorem, except for the special case where f of A equals f of B. Okay, so this is f of A equals f of B. So that's that. It was Eric, it was you, right, who asked me about that?
Yeah, I was just curious about that because well, when I watched the video, I saw the Rolle's theorem went first. I saw that the slopes were 0 at the maximums and at the critical points.
Yeah.
And then when it went to the next one, I saw that maybe I was just confused on the drawing, but I saw that they were slanted, so I was confused on that, but I didn't know if it was at the actual critical points or not.
Yeah, so here's the thing. In the general mean value theorem, we don't actually have to have A equal to B. So consequently, that slope can be anything with anything. So it oftentimes, most of the time, will not be at the critical points, okay? But with Rolle's theorem, it has to be at the critical point.
Okay.
So basically, it has to have f prime of C equals 0.
So Rolle's theorem basically has an extra criteria it has to meet.
It absolutely does. Rolle's theorem has an extra criteria, and we're going to get to that in just a second. We're going to kind of work through that too. Okay? Great question, though. Really nice, Eric. All right. So, let's see. Any other questions about that? We're going to go in and we're going to kind of like do a couple of examples here to kind of clarify some of this. All right. Okay. So let's say, for example, I have f of x. Right, so here's an example. And I have f of x equals, what I want to do is show that, or verify, that's what it actually normally says, verify the mean value theorem for, okay, the function on the interval and then, yeah, function on the interval. That's it. That's all we're going to do. So we'll let f of x equal x squared minus 2x, or x cubed, excuse me, x cubed minus 2x squared minus 4x plus 2. Okay. And we'll take the interval. We're going to have the interval go from 0 to 6. Right? So 0 to 6. So that's our question. So take a minute to write that down. Okay. So now what we're going to say, the mean value theorem is first, we've got the requirements. Right? Like any other proof, we're going to have some requirements. Okay. So one, f is continuous on 0 to 6. Okay. F is continuous on 0 to 6. Yep, great. So is f continuous on 0 to 6? Given that we've done some makeups, tell me, and then tell me why. Okay, yep, it is. Yep, That's right. Everybody got this? F is continuous on 0 to 6, as F is a polynomial, and so it is continuous everywhere. Right? So that's the first part. We need to show that, we need to actually make that statement. Okay? Then 2, we need F is differentiable. So that means that we can find a derivative. F is differentiable on the open interval 0 to 6. Okay? And this might be, we didn't focus as much on this, but is F in fact differentiable on 0 to 6? Yes, it totally is. Why? And it's the same reason, yes. So F is differentiable on 0 to 6 because F is a polynomial, right? And so differentiable everywhere. Great. Okay, so we know both of those things, right? So those are our 2 requirements. And then now what we need to do to verify the mean value theorem, we actually need to figure out what that slope is. So the next little step here, it's not, these are our requirements. So that's like, consider that step 1. And then we need to find f of b minus f of a over b minus a. So we need to find that slope. So I'll give you a moment to do that. Alrighty. So this is going to be f of 6 minus f of 0 divided by 6 minus 0. Just to make sure that everybody's on the same page in terms of the values they've got. And this will end up equaling 120 minus 0 divided by 6, and that's 20. There we go. Very nice. All right, so according to the mean value theorem, right, and this is our statement, there exists a point C in, and that just means belonging to, or you can write in, C belonging to 0 to 6, okay? So that's the x values, such that f prime of C equals 20. So that's the verification of the mean value theorem, okay? And that's that. So if we look here, I'll draw a little picture of it. Just give you a second to finish writing that up. And so that's the entirety of a verification of the mean value theorem. We're going to do a little proof at the end of this, and actually, kind of something that's really handy for those people who are not, well, it's a valuable proof technique to show you how math actually gets done. And for you math people, this is something you will do a lot of, okay? got that? Let's just take a look at a picture of this, okay? Now here's my picture, okay? And I know actually my value is going to go from 0 up to 120. So let's imagine this is 120. I'm just going to imagine that, and here's 6. So that's 6 right there. So 0 to 6. We go 0 to 120. And since this is a cubic function, it basically it's going to look something like that. Okay? It's going to look something like that. Pretty steep slope. It's got a slope of 20. So that's pretty hardcore. Right? Really steep slope. So there's the slope. Okay? So in this case, that tangent line, clearest line in the entire world. Let me clarify the line a little bit. Let's imagine it does one of these things, okay? And then here's the slope between the two, okay? So there's the line. That's the tangent line. Run it. That is a terrible line. I'm going to get a straight edge. That's better. All right, so there's our tangent line. And so that m equals 20. So somewhere along the lines here, right, so probably right about here, I suppose, we're going to get, well, actually maybe even a little further up, okay? A little further up. We're going to get a tangent line to the equation that's going to equal 20. So the slope of this tangent line, okay, the one that I dotted, is going to also have a slope of equal to 20. And that's what the mean value theorem is telling me. If I look at this, right, what I'm seeing is that if I have those two requirements, right, if I have that f is differentiable on the open interval, f is continuous on the closed interval, okay, so those two requirements, then I have the mean value theorem ends up holding true. And for us, the verification is just to show that slope, the f of b minus f of a over b minus a, okay, that slope, what it is, and to just state, you know what, I know somewhere, I don't know where, but I know somewhere, okay, that I am going to end up with a slope equal to that value, okay? All right, let's take a look at one. Let's use one where we're going to use rolls, okay? We'll utilize rolls. So take a look at what you have written down for your rolls theorem. All right.
Hey, Professor.
Yeah, what's up?
At the top, when you plugged in the 6, were you plugging that into the original equation or to the derivative?
Into the original equation. Yeah, okay. See, it's f of b, so it's not f prime of b, it's f of b. Okay. So this is the difference in the y's over the differences in the x's.
Okay.
That make sense?
Yeah, just because I saw that you wrote that such that f prime of c is equal to 20.
Yeah, but that's actually a really key point here, is that it's not saying that f of c equals 20. It's saying in the conclusion, it says that f prime of c equals 20. So that the derivative is 20.
Okay.
So the conclusion is the derivative. But up here, you're utilizing the function itself to find the slope.
Okay.
Yeah.
All right, cool. Thank you.
Oh, f is 0. It's not 0, it's 2. How did you're totally right. You were not tripping, Danny. Ugh. I got all excited that it was going to be like a nice even number, but it doesn't. Yeah. No, it's 2. Yeah. That's 2. I even have it written down on my page. So this ends up being 118 over 6, which is like 19.66 or 19 point. 19.66667.
No, Professor, it's 122 minus 2. F of 6 is 122.
You're totally right. It is 20. Ah, I have that written down too. Okay. Yeah, it's 122. It's the same darn thing. Danny, you have to include that it was 122 minus 2. Same. Yeah. You guys are great. Very right on top of things. So this actually should be, we'll call this is 2, and here's 122. There you go. Same deal, same result, right? But there we go. All right. Okay, so let's go back. Let's do one with Rolle's theorem. Okay, so in this case, right, let's have, right, verify Rolle's theorem. And it'll be the same function, f of x equals x cubed minus 2x squared, okay, minus 4x plus 2 on, in this case, we're going to do negative 2 to 2, all right? Now, Rolle's theorem is going to have 3 requirements, okay? It's going to have the continuity requirement, okay? 2, the second requirement is going to differentiability. That's the second piece, okay? So you're going to have to make sure it's differentiable, but we already proved both of those in the previous question. And then 3, we're going to have f of a equal to f of b, right? So we need to have that be true as well, right? So we already proved this, and then our result is going to be, think about it, right? Then for a point C, in this case belonging to negative 2 to 2, there exists, okay, so there, f prime of c, excuse me, f prime of c is equal to 0. Okay, so f prime of c is equal to 0. All right, so now all I need to do, I've got continuity. I did that in the question 1. We proved that one already. Differentiability, did that one already for question 2. Okay, now f of b, we just need to prove this. Guess how you're going to do that? Yep, plug and chug. Plug in values, see that they're equal. That's it. Negative 2 and 2. Yeah, exactly. You want to use the endpoints, right? This is a to b right here. By the way, this thing right here is a to b. It's the interval. Okay? That's great, Christian. Could we please do mean value theorem? Well done. Okay. All right, guys. Back to here. All right. So what is f of a? And what is f of b? Anyone? There it is. Thank you. Yep. Negative 6, f of a. F of b is negative 6. So f of a equals f of b. All right? All right? That is using Rolle's theorem. Okay, so by Rolle's theorem, there exists a C belonging to negative 2 to 2 such that f prime of C equals 0. Now, the second piece of a question, something like this, is to find C. So now we want to find C, okay? I was talking to somebody a little bit earlier today, and we were talking about like, just you get into a testing environment and you're like, oh, I got these problems. How do I deal with them? Okay, this is an opportunity to practice. Before you even start sitting there and like going, oh, what am I going to do here to find C, right? To find out what C is, think about the problem. Think about what's being asked, right? Okay, and think about the information that you're being given. All right, so the information that we have here, we're going to find C, and what do we know about C? What do we know about C? Take a look at everything that we've got.
F prime of C equals 0.
Yeah, right? By Rolle's theorem, F prime of C, okay, tell me, why, Valet? Why is that true?
Because
It's not a hard question, just simple reason. How'd you know?
the theorem proves it plus because f of a equals f of a and f of b equal each other.
Yes, the theorem just proved it, right? You just proved that F prime of C equals 0, okay? Now, so the next question is, what do I do to find C?
Yeah, set derivative equals 0. Yeah.
Yeah, okay? Think about that, right? If F prime of C equals 0, right, then to find C, you're going to set the derivative equal to 0. So what do we need to do? We need to find the derivative and set it equal to 0. See, there it is. If we just think it through, we already know exactly what it is that we need to do. We're done, okay? It's a logical process. I know by my proof that F prime of C equals 0. Great, okay. And I'm looking to find C. Oh, I'll take the derivative and set it equal to 0. All right. You guys just took a test on this. I think you can do it. Go. Then you can tell me what C is. Okay. There's two places. That's it. So F prime of X is going to equal 3x squared minus 4x minus 4. Okay. And so what that'll give me then, I've got 3x, 2x, okay, 3x, 2 and 2, minus, so this one is,
What's this 2x for?
huh?
What's the 2x? It should just be x.
Because I'm getting my, yes, thank you, it's just x, that's right, absolutely correct. And then this is a 2 and a 2. That's why I was like, okay, there are 2 and 2's at the end, I know that it is. This is going to be a minus, this will be a plus, equals 0. So 3x plus 2 equals 0, and x minus 2 equals 0. So x will equal negative 2/3, and x will equal 2. And those are our c's. Or actually, why don't we call them c's? Well, that's fine. We'll call it c. Yeah, no, let's do that. Okay, so we'll let 3c plus 2 and c minus 2, right? Because we're going to plug in c. And so hence our c's are equal to negative 2/3 and 2. All right, so that's utilizing Rolle's theorem. Okay, so we verified the mean value theorem, which is kind of a big conceptual idea inside of the math. It's going to help us a bit later on. Okay, and then Rolle's theorem is basically used in order to find some roots. Okay, so it helps us to find roots. Okay, so let's do this. Let's take 5. Okay, let's take 5 minutes. And by the way, this one does have 2. It has 2 places where it's equal to 0, right? Both, this is important, both negative 2/3, or excuse me, both negative 2/3 and 2 are in negative 2 to 2. So they're both in there, okay? So you have to include both of them. If one of them wasn't in there, then you wouldn't, right? You'd only include the one that's actually in the interval. All right, so let's take 5, be back at 11:45. We got a little bit more with the mean value theorem, and then we're gonna go into graphing. Boom, boom, boom. Okay, so head into the breakout rooms. And that way you can just discuss, in case any of you guys forgot what the IVT said in the weekend. Okay? All right. So I'm opening up the rooms, head on into the breakout rooms. You're going to show x cubed plus e to the x equals 0. Okay? So basically you're just going to show that it has one real root. So use the IVT to show that the root exists. And I'll give you about 7 minutes to do that. All right, make sure you head on in, guys, into your breakout rooms. Alea, Misha, Minerva, John. Once you've written down the question, or, you know, it is also in the notes. Please head on in there if you can. Start out with this one here. Hey, folks. Just wanted to come in. You're doing the intermediate value theorem. So what does the IVT actually say? So Flora, what does the intermediate value theorem say?
The first step says that f is continuous on, shouldn't we have an interval for this? Or that's not always the case?
It's not always the case. That's right. Okay. So the intermediate value theorem says, right, on a particular interval, what? So like, give me a little bit more. What does the actual theorem say?
It's continuous, and then we have, for step 2, we have to plug in both, let's call it a and b to the function, and see if like they both fall into the interval.
Okay.
And if so, then 0 is between f of both numbers.
Okay.
So by the intermediate value theorem, there exists a c on the interval such that f of c equals 0.
Okay. Yeah. Okay, great. So let me kind of revise a little bit what you just said there. So on the one hand, the intermediate value theorem says that if f is continuous on an interval, okay, and in this case, f is going to be continuous everywhere. All right, if we kind of look at that, you kind of think about that for a minute. If f is continuous, okay, on a particular interval, yes, and we have that a particular number is between the two values on an interval, right? So it's continuous on an interval a to b, and c is between a to b, then we know that the function must equal f of c somewhere in between f of a and f of b. Okay, so somewhere in between those values. So basically, in this case, right, we look at this particular problem, all right? And we say, okay, well, I want to see is 0 in an interval, right? True?
Yeah.
Okay, so I want to see if 0 is in an interval.
Yeah.
So I need to find an interval where when I take f of the first part of the interval and f of the second part of the interval, okay, right? It's got 0 somewhere in that interval.
Yeah.
Does that, you guys,
Okay.
does that make sense? And if I could do that, then I know that 0 is going to be somewhere in that interval. All right? I'll help you out here. Try -1 and 1.
Would that be like, so -1 is greater than or equal to, and then the function? Is that it?
Okay.
Or,
Basically, what would happen is no, you'd say, okay, well, what is f of -1? All right, so let me pop this open here a little bit.
okay,
Right, so we'd
what
say-
you're saying.
Yeah, no, I know. So we're going to we'll pick an interval, okay? Pick an interval, and I said to pick -1 to 1 as a good interval to choose. So we'll find f of -1 and to f of 1, right? And see that interval. If 0 is in here, okay, then by the IVT, right, x cubed plus e to the x has a 0 in -1 to 1. Does that make sense? That's the intermediate value theorem.
Okay, yeah.
Okay.
I just got a little confused since we didn't have like an interval.
Yeah, in this case, right, and we did some homework assignments in which we actually didn't have the interval, right? There were homework problems, and you just had to figure out what the interval was. Generally, like if you look at the equation, you can go, oh, well, let me try out a couple numbers. Okay, does that help?
Yeah.
Does it help, Ricardo, Gabriella, Sheremiah?
Yeah.
All right, cool. All right, see if you can get that written down. We'll pop into this one. Hey, folks. So did you guys, use the IVT to show that there was a real root? Yes. Okay. How about you, Nick? Did you get one? Did you use the IVT to show that we actually we're going to have any real root?
Oh, hey, sorry. I was a little rusty, so I was looking it back up, and I
good.
was in the middle of on it right now.
Awesome. That's perfectly fine. That's exactly why we're doing it. Okay, Kimberly, how you doing?
I'm trying to figure it out.
Okay, cool. So do you understand what the IVT is actually saying? So we want to make sure that that's what it is, right?
It's like if it's in between two, like if it's in between 0 and 0, it has to be 0.
Okay.
Oh no, that was the wrong one. Sorry, that was the squeeze theorem. Intermediate value theorem is I can't. Okay, I know what it is now. I can't explain it. Give me a second.
All right, gotcha. How about you, John? It's like an intermediate value theorem. Okay, all right. So what we want to think about, okay, if you remember the intermediate value theorem, okay, is stating that if we know that if we have an interval, okay, so we choose an interval, and in this case, you're going to choose an interval. I'll give you a hint on one of the ones that you can use, unless Christian already knows it. If we choose an interval, right, okay, and we know that first, f is continuous, so we set up f of x equals x cubed plus e to the x. Okay, so let me actually just do this real quick. Okay, so we're going to set up f of x equal to x cubed plus e to the x. Okay, we're going to have to show that f is continuous. And we're going to have to also show, right, that 0 belongs to some interval a to b, okay? Or excuse me, some interval f of a to f of b. And you need to choose the a to b. So I'm going to tell you that a should belong to, and just here's a good one, -1 to 1. Okay? If you use -1 to 1, you should be able to find a 0 belonging to a to b, and then that actually tells you, in fact, that you're going to get some value. Okay? Yeah. It's kind of, you know, if you think about it, okay, if you think about it, it's kind of like, well, it takes a little thought to think about what the interval is, and hence why I kind of gave it to you. But the idea here is that if you have a continuous graph, okay, something that looks like that, somewhere in here, right, and here's A, here's B, here's f of A, and here's f of B, okay, somewhere in here, because it's continuous, you're going to hit C, right? You're going to hit f of C. So there's going to be a 0 in there somewhere. Has to. Okay? All right. Cool. Any other questions on that? All right. Boop. Okay.
Wait, so you showed that with like a diagram. Can you also show that mathematically? I think there was a, like if you plug in the values or something like that.
Yeah, sure. Well, one, we have to show f is continuous, and that's an argument. Is f continuous?
Is this, oh, you mean x cubed plus e to the power of x?
That's right.
Yes.
Yes, it totally is. Yeah, because x cubed is a polynomial, that's continuous. E to the x is a exponential, that's also continuous everywhere. Add 2 continuous functions, you get another continuous function. Okay? So then 2, all right, we'll let, right, a to b. You know what? I'm going to do this right now. I'll do this in the class right now. How about that?
Okay, sounds good.
Yeah, yeah. Okay. So we'll start with the f is continuous. All right. So let's see. Stop share. All right. Oh, got it. Okay. All right. So everybody should be back in. Okay, so let's take a look at this. All right. So if you remember the intermediate value theorem, it shows that a function will take a particular value for f on an interval given continuity. Okay. Right. So the first thing that we need for the intermediate value theorem is 1, okay, so here's the requirement that we have for the intermediate value theorem in order for it to be true. We have f must be continuous. So we're going to set up f of x equal to x cubed plus e to the x. All right, so that's our first requirement. So f is continuous, right, as x cubed is a polynomial, and e to the x is an exponential, and both are continuous everywhere. So by addition, f is continuous. Okay, right? So by addition, f is continuous. All right, so that's our requirement. Then the other requirement is we need an interval. Okay, so the other one is we need an interval a to b, all right, such that such that 0 belongs to f of a to f of b. F of a to f of b. So we need that as well. That's the second requirement that we have. Oh, sorry. It's a little skittish. All right. So I'll choose -1 to 1. A to b, b -1 to 1. Okay. So f of -1 is going to equal -1 cubed plus e to the -1, which equals -0.6321. F of 1 is going to equal 1 cubed plus e to the 1, which equals 3.718. So that's our f of a to f of b, right? That's the f of a to f of b. So 0 belongs to, okay, -0.6321 to 3.718. All right, so what we now know is that our f is going to be belonging to that. Okay, so by the intermediate value theorem, f of c equals 0 for some c belonging to -1 to 1. And that then tells me that I have a root that exists. So I now know that a root exists, right? I have at least one of them. So I now know that I have a root exists, right? So basically what I showed was that I created a function, and the function was basically the same one as in my question. F of x equals x cubed to e to the x. And then I found an interval where the y values, right? Consider this as y1 and y2, that somewhere in y1 to y2, right, there was a 0 in there, right? And I had to pick the right one, okay? But I did that. And then that showed that means that the function has to take a 0 somewhere. It has to be 0 somewhere. So we're good. So we know that a root exists. Now, getting to the new stuff, okay? Now we want to show that, use Rolle's theorem to show that it is the only root, okay? And this is a little bit trickier, right? But you got a little homework problem where you do this, but I'm gonna do that. Can I move on? Does everybody get this written down? It's also going to be in the notes. Okay. All right, so now when I use Rolle's theorem to show that it is the only C. So let's remember, Rolle's theorem says that if f is continuous and differentiable, and f of a equals f of b, okay, then there exists a C belonging to A to B such that f prime of C equals 0. All right. So basically, there exists some kind of minimum or maximum on that graph or on that function, right? So what we're going to do is we're going to notice that we're going to see that we're actually positing that there is no A and B, right? So we want to show that there is no A and B. A and B, okay? So only one value such that, okay, f of A equals 0 and f of B equals 0, all right? So if you think about that, we wanted to show that there's only one root, okay? So the whole idea here is that if we've got two different values that both end up equaling 0, then that means that we have two roots, and that doesn't work, okay? So what we're going to do is that we're going to show that there's only going to be one of them. And the way that we're going to do that is we're going to do this by showing that f prime of C will never equal 0. So if f prime of C does not equal 0, then there is only one root. All right. So let me just tell you that this is kind of a deep thought, right? You have to kind of think about it. Like, it's not that kind of like, let's do this kind of problem kind of thing. This is basically what we call the contrapositive of the statement. If f prime of C does not equal 0, then there is no such f of A equal to f of B, right? That's essentially what's saying, right? The Rolle's theorem says it one way. We're now going to say it the opposite way. So it's going to take some thought. You might have to go home and study this a little bit, okay? In fact, I would say you probably would. I would. That's what I would do. Okay? Because you're just going to have to think about it for a while. But this whole idea of showing that f prime of C cannot equal 0, that we can do, okay? The logic is hard. The process, not so hard. So we have f of x is equal to x cubed plus e to the x, right? Yep. So f prime of x is going to equal 3x squared plus e to the x. Can this ever equal 0? And then, even more importantly, why not? Even more importantly, why can that never equal 0? So the answer is yes, no. This can never equal 0. Yep. Well, yes, it's undefined at 0, but we need to know why. It has a horizontal asymptote at x equals 0. That's true. Okay. This can never equal 0. Although having a horizontal asymptote doesn't necessarily mean that x can never equal 0. you could actually have an end behavior asymptote, and you could cross it. So, because look at the function. Yeah, look at the function. 3x squared. What do we know about it? What do we know about e to the x? Yep. So 3x squared is always going to be greater than or equal to 0. And e to the x is strictly greater than 0. So 3x squared plus e to the x is strictly greater than 0. Think about that for a second. Deep, deep thought. Not so deep, actually. It's probably, you're like, that's totally obvious, right? So 3x squared plus e to the x will never equal 0. So there is only one root. And we should say only one unique root to e to the x, or x cubed, plus e to the x equal to 0. All right. Challenging. I have to go home, think about it a little bit, do a little bit of work. Like, any questions on that right now? You might have other questions. But this is basically, this is kind of showing us what is it that Rolle's theorem does, and what is it that the mean value theorem does. It tells us what kind of derivatives we can expect on particular intervals. Okay, that's what the mean value theorem does. That's what Rolle's theorem does. It tells us what kind of values we expect on particular intervals. Okay, all right. Let's take an 8-minute break, and then we're going to go and hop into graphing. Okay, so please be back at 12:20. Sorry. All right. So let's take a look at, now we're going to go on, we're now popping into 4.3, and we're going to start talking about derivatives and graphing, which is one of the big topics, the big ideas here from this particular section. Okay. And so, or not this particular section, but this chapter is, a lot of this chapter is about functions, graphs, and understanding what we call a real analysis, analysis of the function. And so what we're going to do is we're going to break up this function, and we're going to start talking about how does understanding things about the derivative play a role in understanding the function better. All right. So you've done a lot of this already inside of pre-calculus or inside of your college algebra course, but now we're gonna take it to another level. Okay. We're gonna take it to another level where we're gonna add in the derivative. So as I talked in, as we've actually talked quite a lot before, when we talk about increasing and decreasing, okay, what we're going to talk about here, and also inside of the video, is increasing and decreasing has to do with the first derivative, right? Okay. So we've got this, f is our function, and whether or not it's increasing or decreasing is going to be dependent upon the first derivative, okay? So let's start out, what we want to do to find these intervals is we want to find, right, okay, when f prime of x equals 0, which we have another name for that. Those are called our critical numbers, okay? F prime of x equals 0, and when f prime of x is undefined. All right, so let's start out on that. I'll give you a minute, a couple of minutes to go and do that. Well, first, actually, why don't we just do this? Right, find f prime of x. That shouldn't be too terrible. So f prime of x is going to end up equaling 2e to the 2x minus e to the negative x. Then, okay, so we'll look here, and first, the domain of f prime, okay, is all real numbers. Okay, so we've got all real numbers, that's the domain, so the derivative is defined everywhere. So we don't have that as a critical number. Now let's see, okay, when 2e to the 2x, right, minus e to the negative x is equal to 0. Well, that's going to be when 2e to the 2x is equal to e to the negative x. Okay, we'll do a little bit of algebra here. Okay, so I'm actually going to divide by e to the negative x. So that's going to give me 2e to the 3x equals 1. So e to the 3x equals 1/2. All right. Hopefully, you folks out there are getting a lot better at working with these logarithms. Right, so that means that natural log of e to the 3x, which is just equal to 3x, equals the natural log of 0.5. So we'll just let x equal natural log of 0.5 divided by 3. So that's our critical number, okay? That's our critical number. We need that one, okay? Now what we want to do is want to go in and we want to check. This is just like, if you remember the velocity problems, velocity, right? Positive direction, negative direction problems. This is exactly that. When we talk about velocity going in the positive direction, we're talking about f increasing. And when we're talking about velocity in the negative direction, we're talking about f decreasing. So they're actually the same question, just a different context. All right, so we'll have natural log ln of 0.5 divided by 3 right here. And by the way, this is approximately negative 0.231. So let's test some points. Go ahead, go in there, test some points, right? And then tell me, put into the chat, right, what our increasing interval is, right? That'll be our positive direction interval, increasing interval, and which one will be our decreasing interval. So which one's negative, which one's positive? Put it up into the chat when you're done, okay? So write the interval out, okay? Figure, like, first test the points, all right, on either side of natural log of 0.5 over 3, then determine on which side is it negative and on which side is it positive. And by the way, you're testing f prime in this case. First derivative. All right, give me the interval. Interval of A. I said ask for the interval. Okay. The interval on which it's increasing and the interval in which it's decreasing. So I'll take, for example, f prime of 1, f prime of negative 1, okay? And that ends up equaling, right, e to the negative 2 plus, or excuse me, 2e to the negative 2 minus e, okay, to the 1. That ends up being negative. Negative. So that's just giving an example of what I did. Okay. Okay. 1's great. Negative 1 equals, there you are. Okay. Anybody else? Great. That's true. All right. Nice, Mina. Then I'll take Mina's f of 1, or actually, I get Valet's is the one I used. I used f of 0. So f of 0 ends up equaling 1. So it's 2 minus 1, which equals 1. Right? So it's positive on this side. Okay, that means that from 0 to natural log of 0.5 over 3, we are decreasing. And we are increasing over here. Okay, so given that that's the case, right? Okay, so f is decreasing from negative infinity to natural log of 0.5 over 3, and increasing from natural log of 0.5 over 3 to infinity. Okay? Decreasing on the one side, increasing on the other. All right? Cool. So tell me, all right? Any questions on that? Pretty straightforward. I mean, like, well, it is very straightforward. Find the critical numbers, test points on either side, on any side of the critical numbers. No. Well, hard to call it a vertex, Danny, because this is it's just a local minimum or a local maximum, which we'll talk about in a moment. It's a vertex. Generally, we're going to talk about a vertex in reference to a parabola and a parabola only. So consequently, this is not a parabola, so we really wouldn't call it a vertex. That follow? So we'll call it more specifically a relative extrema. All right. So let's ask ourselves now, all right, what's the local minimum and maximum values? And then why? Okay, so I'm going to add in the why. All right. Let's try this out. Hey, Rashi? Can you talk? Yeah,
Yeah.
great. What are our local minimum and maximum values? Any thoughts? Like anything that you might be thinking about?
So
Sorry, I put you on the spot. I just figured you'd be okay.
I'm sorry, I'm like a bit unsure.
That's okay. There's nothing wrong with unsure. How about tell me what you're thinking about?
So is it like the point where it's decreasing would be the minimum and then where it's increasing would be the maximum? Or
Okay. All right. Gotcha.
like would it, yeah, sorry.
So no, that's okay. So here's the thing, right? Okay, if you ask yourself, is it decreasing within the interval, okay, or increasing within an interval? Like when we talk about where is it increasing, where is it decreasing, that's not at a point. That's generally at an interval, right? We could talk about it in a point, but like it's generally at an interval. Our local maximum and minimum values, okay. And so this is a good question, Nicholas. Nick asked, is it a max and min values within an interval? Well, it's within for the entirety of the domain for the function, okay?
So would it be where like the slope would be like 0 or?
There it is. It's going to be where the slope equals 0. The slope of the tangent line equals 0. Yes.
Yeah.
Great. Okay. So that's, by the way, it's not necessarily, that's not going to necessarily be a local min or max. Okay. We're going to have an extra little piece. Okay. It'll be a critical number. That's exactly it, Danny. It's going to be a critical number. So where is our critical number? Sorry if that was, yeah, it's going to be where f prime of x equals 0. Nope, actually there is one. Okay, let's take a look.
Of 0.5 over 3? Or?
Yeah, so it's going to be this thing right here, okay? Think about what we found. Natural log of 0.5 over 3. Good, Rashi. Stick around though, you're fun to talk with. So if I have natural log of 0.5 over 3, okay, I know that that's where the derivative equals 0. So it's a critical number. It could be a max, it could be a min, okay, or it could be nothing. I don't know, okay? Does that follow? It could be one or the other. Yeah.
So if it's between like a negative decreasing and a positive increasing? Like if it's going from negative to positive, would that determine whether it's like a max or min versus if it was the other way? Or does that not?
That's a great question, Rashi. Everybody think about that for a second. If on one side, right, on the negative side of the critical number, it's decreasing, and on the other side of the critical number, the function is increasing, what does that look like? Can we see your picture, Rashi? Is that okay?
My picture?
Yeah. Turn on your video. Is that all right?
Oh, sorry, 1 second.
If you're not, it's okay. I can do it myself.
Is it a?
You just muted yourself.
I kind of was picturing it as like a x cubed function. So like, I don't know how to. Sorry, 1 second.
Sure. Everybody should be. It is a cube function. I just want you to think. All right.
Like, I don't like. This is like a really bad drawing.
Okay. You don't have your video on there, Rashi. Okay, let's see.
Like, maybe like that.
Kind of, except there's that e to the x portion, so it like flattens completely out. Okay, right? It does an interesting thing. Here's the idea. Okay, very nice. Thank you. You can turn off your video again. I just wanted to kind of like watch. Decreasing, critical value, increasing. So what is it?
A parabola?
Okay, but what is the point? The point is it's not actually a parabola.
Oh,
It's a minimum. You guys see that? It's a local min. If you decrease and then you increase right afterwards, it's got to be a local min. Versus if we increased on the negative end and then decreased, it would have to be a max. So what is happening on either side of the critical number determines whether or not it's a minimum or maximum. Okay? So if we think this is increase, and then we hit the max, and then we'd start to decrease. Well, that's what a max has to do. So one of the things that so you guys were like, it's a cube, I'm thinking about it as a cube, I'm thinking about it as a parabola. Well, one, it's not a parabola. We already established that because it's not an x squared, okay? Right? Yeah, we want to visualize. Yes, we want to kind of visualize what it is. And it's not exactly an x cubed either because we've got that e to the x function. What we do want to see is that on the one side, right, on the negative side of natural log of 0.5 over 3, we're decreasing. And then on the positive side, we're going to increase. And since we do that, since we go decrease, then increase, well, I don't know. I think I have to go the other way. Decrease, then increase, right? Then that tells me that I have a minimum. Decrease, hit the minimum, and then increase. Or the other way around, if I increase, right, and then I decrease, then it's got to be a maximum. Yeah, right. That's it. It's the slope. So all these slopes are decreasing. They're decreasing slopes. Okay? And the slope of the tangent line here they're increasing. Right? That's what it tells you, right? When we have it's negative, we have negative tangent line slopes, negative positive tangent line slopes when it's increasing. So that tells me that in fact this is a minimum. So the natural log of 0.5 over 3, comma, f of the natural log of 0.5 over 3 is a local minimum because the graph decreases the graph is decreasing. We might as well say that. The graph is decreasing when x is less than natural log of 0.5 over 3 and increasing when it is greater. when x is greater than natural log of 0.5 over 3. Okay? Key point, very important to think about. Okay, so I tested where it was increasing and decreasing. Now, once I do that, okay, the critical numbers are going to be where I can possibly, but not absolutely, possibly have changes in my my going from increasing to decreasing or decreasing to increasing. And so hence that's why they are going to be minimums and maximums. Okay? And you want to kind of think it through and see, all right, if I go from decreasing to increasing, right, I have a min. And if I go from increasing to decreasing, right, I'm going to have a max. That's right. So the behavior of the graph on either side of the critical number, or the critical value. I keep calling it a value. It's a number, value, whatever. Yeah. Okay. All right. Any questions on that? It's neat, huh? It's going to give us a whole lot of information. Now, intervals of concavity and inflection points. So first question, okay, what is concavity? What is concavity? What do you think, Mina? What's concavity? According to what you understand.
Can I unmute myself?
Absolutely. No, just turn on your video and sign it.
I would if I knew ASL.
There you
go. Concavity, from what I understand, is like I'm doing like sign, but like it's like when it either curves upward or curves downward, like the curve of it.
Yeah, if you want to turn on your video, you can too, and you can show us with your hands.
I'm not wearing a scarf. That's why I don't have
that's
my
okay.
video.
Then don't turn it on. That's totally fine. All
But
right.
yeah, I was using my hand to try to explain. But like, for example, when it's like x squared or negative x squared, like that curve would be the concavity.
So that's concave down, like it has that curvature. Okay.
Mm-hmm.
And then this curvature here, right? That's concave up. Yes?
Yes.
All right. It's where like the U, if the U points downward, it's concave down. If the U points upward, it's concave up. Okay?
Mm-hmm.
Yep.
Okay. Cool.
Oh, Misha. Thank you, Mina. What was your question, Misha? What's the issue? I got a huh? Okay. And, all right. Got it. All right, well, now we do. All right, so it's going to tell us the shape of the graph. So like increasing, decreasing, increasing tells me when it's going up, decreasing tells me when it goes down. Now, what we can get here, right, say for example, is you can imagine that this is increasing in concave up, right? Can you guys see that? It's increasing, or excuse me, increasing concave down. This is increasing concave up, right? So these are both increasing and increasing. Right? Sometimes, yeah. Then this, right, is decreasing and concave down, or excuse me, concave up. Okay, and trying to think of concave down and there it is. And that is concave down and decreasing. So they are both. They're qualities. You have to consider both qualities, right? You'll have both of them, right? You'll have its concavity, and you'll have whether or not the function is increasing or decreasing at that point, right? Unless it's equal to 0, right? Which we'll talk about when we talk about the second derivative test. Okay? Do linear functions have concavity? No, they do not. Nope. And nor does the absolute value of x have concavity either. Yeah, so those are great. Those are two great questions. If you look at this, okay, you know what? I'm going to hold that question for just a second, Danny, and we're going to talk about how we find concavity, and then we'll show why it is that, in fact, linear functions do not have concavity, but they don't. Nor does the absolute value of x, because its absolute value of x is technically a linear function. All right. So, and how do we like? What is it now? What is an inflection point? All right. Yep. It's going to be the second derivative set to 0, exactly. But what is it from a graphical standpoint? What is an inflection point according to what you understand? I mean, what does it have to do with concavity? Let's see. Yep. Yeah. So Raji said it's when concavity changes. That's right. This is an inflection point is when concavity changes. So it's going to be when concavity changes. Okay. Yep. And it's where it goes from negative to positive in the second derivative. Exactly. Okay. So an inflection point is when the concavity changes. Okay. And so like this is, if we think about it, this is equated, okay, to a critical number. And what I mean by that, let me kind of demonstrate what that means. So an inflection point is when concavity changes. Okay. A critical number is when we go from decreasing to increasing or increasing to decreasing, plus a couple of other things. Okay. So they indicate changes. So a critical number indicates changes from increasing to decreasing. An inflection point indicates changes in concavity. Okay. The difference is that an inflection point only indicates changes in concavity. Okay. That's the only place, that's the only value that it's going to give us. Okay. It is possible for us to have a critical number that does not go from increasing to decreasing or decreasing to increasing, right? We talked about that a little bit before, and you're going to have to see some of that in your homework, right? But, right, when we have an inflection point, okay, that inflection point is going to indicate change in concavity, okay? And to find inflection points and concavity, we use the second derivative. Okay? No. Misha asked, is our inflection point one of our critical numbers? No, it is not. An inflection point has to do with the second derivative. Critical numbers have to do with the first derivative. Okay? To find inflection points, set f double prime of x equal to 0. All right? To find concavity, we determine the sign of f double prime of x. Okay? So to find inflection points, we're going to set f double prime of x equal to 0. To find our concavity, we're going to determine the sign, that's what that says, the sign of f double prime of x. Okay? So let's do that with this one. F prime, if you remember, of x was equal to 2e to the x minus minus e to the negative x. And so f double prime of x, the second derivative now, is going to be, and that's to the 2x, excuse me, is going to be 4e to the 2x plus e to the negative x. So let's find our inflection points. I'll give you a minute there. I just got to step out for just 1 second. Find the inflection point. Set f double prime of x equal to 0, and then solve. Okay, so what'd you guys get? Put it up in the chat. Put it in the chat. What'd you get? Interesting. What'd you get, Kira? Really? So 4e to the 2x plus e to the negative x, and you set it equal to 0, and you guys got something? Oh, thanks, Kira. First things first, Ricardo, and this actually goes for all of you. The natural log of a negative number doesn't exist. Oh. True? I believe I'm true. Yep. But it's still working. All right. Before you do any work, before you go to algebra, okay, it's a great example of something like this, Brianna, is we sit down and we go, okay, before we even do any algebra, like you might want to ask yourself whether or not it's even possible, right? So look at this. We got e to the 2x. This is e to the 2x is greater than 0. And e to the negative x is also greater than 0. So 4e to the 2x plus e to the negative x is greater than 0. So it never equals 0. Yep, there's no solution. It can't happen. It is not cheating. That's called math. All right. You guys are becoming sophisticated mathematicians, mathematics people, right? We're developing sophistication. So, right, things like this. Oh. So things like this, they're not tricks, right? They're legitimately things that you should be thinking about. Okay. And so you don't want to just dive into doing algebra. You want to sit down and you want to say, okay, well, can I actually do this? Right? Is this possible or not? Right? Okay. And consider and think before you actually start working. All right. I know that you are thinking. I get that when you do your yeah, that's exactly it, Rashi. It means the concavity never changes. So I know you're thinking, but I want you to like stop and don't do anything for a minute and go, wait a tick. Is this possible? Okay. So yeah. So there are no changes in concavity. So what that means for us is this means either the function is all concave up or all concave down. Which is it? Is it all concave up or all concave down? Valet goes up, right? Why? Why, Valet? You can unmute. Why is it concave up?
Because we had a 0 earlier from the critical number, and then it was all above the critical number. From the
Okay, that's true. So the second derivative test, if you remember from the videos, the second derivative test tells you that we have a minimum, right? So we had a minimum. So that means the second derivative is always going to be positive. Yeah. How about this, right? We just showed it.
It's that's always above 0. Yeah, that's right there.
Yeah, we just showed that it was always above 0. Okay, right? You could do that, or we test a point, right? Let x equal 0. And that gives me 4 times e to the 0 plus e to the 0, which equals 5. So the second derivative is positive. So we went and I tested, right, by this is f double prime of 0. All right, but we showed, okay, this is always 0. That's one way to think about it, right? We also had, if you look at the second derivative test, for those of you who haven't watched the videos yet, bear with me. The second derivative test, okay, is going to say, all right, if I have a minimum, that means that the graph has to be concave up, right? The graph has to be concave up for a minimum, and then for a maximum, it's going to be concave down, okay? So because natural log of 0.5 over 3 is a minimum, that means that at that point, right, okay, we have concave up. But since there's no changes in concavity, that means that everywhere the function is concave up. Cool? And by the way, is this a parabola? No, it's not. It's not a parabola. Just to let you know. Nope, not a parabola. Because parabolas are quadratic. By the way, if you look at it, if you went in and you drew a graph, it looks something like this. It kind of like flattens out at the bottom and then it rockets up on either side. Does one of those things. There we are. So yeah, okay. All right, so just to kind of review this, okay, to review what we basically went over right here is 1, okay, I'm gonna head back up to kind of the top of this. To determine increasing or decreasing, we're gonna use the first derivative, okay? We'll first find our critical numbers and then we're gonna test on either side of the first derivative. We also wanna make sure, okay, and I showed this in one of the videos, that make sure that you actually test also around when f prime of x is undefined, right? When it's not differentiable, okay? So make sure that you do that. Then, all right, so once we've done that, we can determine our local minimums and maximums by determining what the behavior around the critical number is. If the critical number is decreasing to increasing, okay, we're gonna have a min. If it's increasing to decreasing, we'll have a max, okay? And we wanna, kind of define what that value is, okay? Now for concavity, concavity is actually the shape of the graph or the shape of our function, right? We have it either concave up or concave down. It's concave down when, this is when f double prime of x is negative, okay? And it's concave up when f double prime of x is positive, okay? So concave up when f double prime of x is positive, f double prime is negative, then it's concave down, okay? Right? And an inflection point is when the concavity changes. So to determine the concavity, what we're going to do is find all the inflection points and then test around those inflection points. All right. So that's a big part of what we're doing. So we're going to do another example after the break. So let's take 5. Let's get we'll come back at 1:05 and then we'll go and we'll do another example and then we'll call it a day. Okay? All right. Cool. All right. So now what we want to do is we want to take a look and we're going to say, okay, let's look at this function. This is the number 6 on the lesson inside of the notes. Okay, so let's consider the function f of x equals 1 plus 1 over x minus 1 over x squared. So we now have a bunch of things that we can do. So let's start out with, let's find the vertical and horizontal asymptotes. Okay, start with the vertical ones. Yep. So we have a vertical asymptote at x equals 0. Okay, make sure you got that, right? Because x cannot equal 0. And now, what about the horizontal asymptotes? All right. So this one is going to be the limit as x approaches infinity of f of x. And then that's going to equal, right? This will be 1 plus 0 minus 0. So that's going to end up equaling 1. Or let's do 1 plus, this is basically 1 over infinity minus 1 over infinity squared, which is equal to just 1 plus 0 minus 0. Okay? So that's 1. And then our, in the negative direction, so our end behavior in the negative direction of f of x is going to equal just 1 plus 1 over negative infinity now, minus 1 over negative infinity squared. And so that's 1 plus 0 minus 0. And again, that's 1. So that means our horizontal asymptotes are going to be y equals 1. Okay, we're going to have one at y equals 1. So there we go. So that gives me two things that I can actually draw, right? I could draw my horizontal asymptote. I could draw my vertical asymptote. Okay, so that gives me two things that I could actually draw. Okay. Now, next question is to find the intervals on which f is increasing or decreasing. Okay, so consider what we did, all right? And I'm going to let you guys do that. I'm going to give you about, well, first, how about we first start out with find the critical numbers. I'll give you about 5 minutes to do that. Okay, so find the critical numbers first. So don't forget where f prime is undefined. It's going to be also a critical number as well. So wherever f prime is undefined, also going to be a critical number. All right, I'll give you another minute. Go through, check your work. So what I got was I got f prime of x is going to equal negative 1 over x squared. Okay. Yeah. Plus 2 over x cubed. Okay. Okay. So we'll now set that equal to 0. So that gives me negative 1 over x squared plus 2 over x cubed equals 0. And this then is going to be that 2 over x cubed equals 1 over x squared, if we just add to both sides. All right, so that means that 2x squared is going to equal x cubed. All right, we could just divide through by x squared, divide through by x squared, okay? And then that gives me 2 equals x. So x equals 2 is my critical number. All right, check my derivative, check to make sure you got the same derivative. And then check my work. But there it is. Then we also have the undefined one, and this function is going to be undefined at x equals 0. The function is undefined. Okay. All right. Now second part, test. Test your derivative. And just to kind of give you so test your derivative. Gosh, that's terrible. Test your derivative. All right. We're going to have to put in 0 and we're going to have to put in 2. We're going to have both of them. Okay. So go through, test your derivative, right? So you're going to be plugging in values into the derivative. Really important. Okay. Okay. So I'll choose f of negative 1 here. And that ends up being negative 1 minus 2. Okay, which equals negative 3. So it's negative. So that means that we're decreasing on this interval. Okay. Let's choose f of 1 here. That's negative 1 plus 2. So that's going to be positive. That ends up equaling 1. So this is increasing because the derivative is positive. Okay. And then f of 3, okay, is going to be negative 1 over 3 squared plus 2 over 27. Okay. This is just going to end up being negative. So it's decreasing on that side of 2. All right. So if I wrote my intervals, okay, So increasing, right, from, wait for it, increasing from 0 to 2, okay, decreasing from negative infinity to 0, union 2 to infinity. Okay, there's your increasing and decreasing. So that should actually now allow you to say where are the local minimums and maximum values. Now, be careful. I'm going to tell you right now, not a min. That is not a minimum. It's a critical number, but remember what it is. It's an asymptote. Okay? That's not a min. So it's an asymptote. Yep. So we will have a local, what is 2? Is 2 a max or a min? We have a local max, right? Because we're going from increasing to decreasing. So 2 is a max. We have a local max at 2, comma, okay. I gotta plug it into the original function. 1 plus 1 over x. So that's f of 2. And just to say that f of 2 is equal to 1 plus 1/2 minus 1/4, which equals 1 and 1/4. So 2, 1 and 1/4. Okay, that's our local maximum. That's it. Next up, we're going to find the intervals of concavity and the inflection points. So ask yourself, okay, so how do I find, let's start out. First thing we want to do is to find those inflection points. Okay. So I'm going to define f double prime. I'll give you, to find the inflection points, I'll give you about 6 or 7 minutes. All right. So find the inflection points. We want to find when f double prime of x is equal to 0. Okay. And so if I check my f double prime of x was equal to 2x cubed minus 6x, 2 over x cubed, 2 over x cubed minus 6 over x to the fourth. So check your derivative against mine. And then that means that 2 over x cubed, our inflection point, is going to be when 2 over x cubed minus 6 over x to the fourth equals 0. And so that's 2x to the fourth equal to 6x cubed. Okay. You have to be careful, okay? So it's undefined at x equals 0. So we got to be careful about that, right? Okay, because actually this thing is going to have a true statement at x equals 0 as well. So we're going to have 2x to the fourth equal to 6x cubed. That means that, doing a little algebra, we're going to get 2 x to the fourth over x cubed equals 6. And that means that 2x equals 6. And so x equals 3. You have to be kind of careful here when you end up with x's on both sides, like this when you're multiplying, that you have to consider that the value 0 is also going to make this true. So x equals 0 also makes this true. Okay? But we already know 0 is problematic. 0 is problematic because 0 on the denominator, okay, is going to end up being a problem for us. Okay? But let's consider around 0 and 3. Okay? So 0 won't be our inflection point, but we do want to make sure we just check there. So we've got 0 and 3. Okay? And so we're going to plug in for f double prime. So we'll take -1. Okay? So I'll find f of -1 here. Oh, by the way, anybody have any questions about finding the inflection points or why I'm also going to consider 0? Okay. F of -1, okay, is going to be 2 over, let's be -1 cubed. Okay. Yes. Right? F double prime, thank you. F double prime of -1, thank you. F double prime of -1 will be -2 minus 6. So this is going to be end up being -8. So it'll be negative. And that means concave down. Okay. F of, and let's see, F of, call it 1, right? So you definitely don't want to use 0 because you can't use 0. So let's try F of 1. F of 1 is going to give me 2 minus 6, okay? And so that ends up being -4. So it's also going to be negative. It'll be concave down. So in summary, concavity, finding inflection points, are setting the second derivative equal to 0 and then finding your x's. So it's the second derivative equal to 0, and then we find the values for x. Okay. And then we'll try f of 4. Okay. So that's 2 over, say, for example, 2 over 64 minus 6 over 256. That's going to be positive. You can check that if you want. All right. So positive, and we're concave up. So we have an inflection point, okay? Inflection point at x equals 3, okay? And we're concave down, on both sides of the concave down on negative infinity to 0, okay? Because at 0, we're nothing, right? The function's nothing at 0. Union 0 to 3, right? That's because the function isn't defined. The second derivative isn't even defined there. So we have to be like, okay, well, I got to exclude that. It's not going to be concave down at that place. It's not going to be anything, okay? And concave up on 3 to infinity. So that's where it's going to be concave up. Okay. Okay. So now write that down. And then we're going to sketch a graph. We're going to like do a sketch here. Okay. Here we go. And I'm going to put my information here, okay? So I'm going to put, right, vertical asymptote at x equal to 1. All right, excuse me, x equal to 0. Horizontal asymptote at y equal to 1. Okay, so that's going to end up being my end behavior. Okay. The next thing actually that I want a local, I got my local, it was a local max, right? Local max. Got to go back and see what it says. Two, 1 1/4. Okay. Got a local max at 2, 1 1/4. Okay. We were decreasing from negative infinity to 0, union 2 to infinity, increasing, okay, from 0 to 2, right? Concave inflection point at x equal to 3, okay? Concave down from 0 to, or excuse me, infinity, negative infinity, yeah, negative infinity to 0, union 0 to 3, and concave up, okay, from 3 to infinity. Excuse me. There you go. All right. So now I kind of graph my, when I go through and graph, and we're going to do more curve sketching tomorrow, a lot more curve sketching tomorrow. Let me get my straight edge. Okay. So there's that. Okay. I'm gonna, first thing I'm gonna do is I'm gonna put in my vertical asymptote, right? So here, I'll just put that in red. Okay, shirt, draw, red. That way you guys can see. So there's my vertical asymptote. Okay, horizontal asymptote at y equals 1. Okay, local max at 2, 1 1/4. So 2, and then it'll be 1 1/4. So there's a local maximum right there. So I'm going to draw this. I'm going to decreasing from negative infinity to 0, okay, and concave down from negative infinity to 0. So what that means, if I'm decreasing and concave down, got to be down here. It's got to look like that, okay, because we have that horizontal asymptote going towards 1, okay. We have the decreasing, and then we have, notice it's concave down, so it's got to look like that, okay. I have a point of inflection at x equals 3, okay. And since this is a local max, x equals 3 has got to be below that. So let's actually figure out what x equals 3 is, just for the sake of drawing the graph properly. F of 3 is going to equal 1. Right, 1 plus 1/3 minus 1/9. Okay. Okay, 1 plus 1/3 minus 1/9. So that's like 1.22222. It's just slightly less. It's just like barely less. Okay. And in fact, so what that means is that, so we've got increasing, right? We've got increasing up to 2. So we've got this vertical asymptote here. So we're increasing up to 2, yet concave down. Notice concave down. So it's going to be concave down, right? We'll still continue to be concave down as we come around the 2, okay? But then on the other side of 3, we're going to go concave up, and we're going to start pushing towards the horizontal asymptote. Okay, so we go up, hit the max, okay, and then we should start pushing towards the asymptote. So that's our graph. Now take a look a couple places. Notice concave up here from 3 to infinity, concave down here from 0 to 3, okay, increasing until we hit 2. Okay, so we increased until we hit 2, and then we decreased from 2 to infinity. And so that completes the graph. So definitely tonight, okay, you want to make sure, because tomorrow we're going to curve sketch, okay? So definitely tonight you want to like practice some of this, taking the first and second derivative, finding your inflection points, finding your critical numbers, okay, determining whether the function is increasing or decreasing, okay? Yeah, because it's going to come in, it's going to play out very, very importantly tomorrow, right? You'll be well on your way tomorrow if you actually go in and, you know, kind of do this kind of thing. All right. Okay. Any questions on this right now? Drawing the graphs takes a little bit of practice, but then it's all a matter of when you get done, check to see if your graph matches all the information that you've taken down. All right. So let me give you some marching orders for tomorrow. Okay, I'll put them up in an announcement. All right, so here's some preparation for July 8th class. Okay. 1, watch the videos for 4.4 and 4.5. Okay, so watch the videos for 4.1, 4.5. Okay. If you want to do the readings, you certainly can. I think this last one, it was better to do the readings. Skim 4.5 and look at the requirements for sketching graphs, okay? Make sure that you can do all of those requirements. So of those requirements, there are a set of them. They're also in the videos for 4.4 and 4.5. So you probably want to just make sure that you can like find a domain, okay? Find intercepts, determine symmetry, okay? This is, it's from chapter 1. So I have some videos inside of the modules here for chapter 1 if you want to see that, even and odd functions, and then periodic functions. So make sure that you're good with those. Review horizontal and vertical asymptotes. And then increasing, decreasing, and increasing, decreasing, concavity, and that's, you know, local mins and maxes, excuse me, local mins and maxes. So all those things, you kind of want to make sure that you go through and you review those to make sure that you can, you know, that if I start working with them and we're, you know, like I'm like, hey, find the intercept for here. You're like, oh, I know what he means by that. This would be X and Y intercepts. Okay. When it comes to for 4.4, all right. For 4.4, basically what we're going to be doing is we're going to be using another method in order to find limits. So we're going to use the derivative in order to find some limits. These undetermined limits or undefined limits that we had previously before. And so rather than using algebraic tricks, we're going to use something called L'Hopital's. So just make sure that you watch the videos for 4.4. Okay. Do your homework for 4.1, 4.2, and 4.3. All three of them, 4.1, 4.2, and 4.1 and 4.3 are definitely going to be helping you with tomorrow's work, okay? Because tomorrow's stuff on curve sketching is going to be all about that, okay? So you want to make sure that you at least get some opportunity to do some review, do some practice with what we've done today, and post any questions for tomorrow in the discussion board. Okay. As a side note, I am furiously working on grading your exams. I'm thinking probably by Thursday morning or so, Thursday or Wednesday night, Thursday morning, somewhere around there. I'll post the rubric, the answer key rubric, either later tonight or tomorrow. Okay, and that way you can go in and check it against what I got. Don't forget also that there is a makeup exam for chapters 3 and 4. Okay, and it's the last week of class on that Monday. All right. Okay. One last thing is for this semester, we are not going to be doing 4.8. Okay. So the next exam, that I should add that in. The next exam is on Monday. It'll be 4.1 through 4.7. Practice exam will go up today. I have that almost done. Okay. All right. Any questions? Okay. Thanks, Carla. You're welcome. All right. Have a great one, guys. I'll see you tomorrow. You guys are doing great. Keep sticking with it. Okay. Thanks, guys. Everybody's doing well.
Thank
Have
you,
a great
Preston.
day. Yes.
See you tomorrow.
See you tomorrow, everybody. Kiara, just use that link that I sent you to meet me in my office. I'll be in just a minute, okay? So you can just use that link now.
A quick question. Your office hours, I was looking on the syllabus. I didn't see them. Is it just after class generally?
I don't generally have office hours. The people requested to see me after class. So if you need to, you can make an appointment. I don't have office hours during the summer.
Okay, so
Okay.
like I'm trying to figure out if you'd be open. Not now, I don't need it right now. But like if I had homework, help, or questions, I could go to you after class or something.
Yeah, I mean, like after class, you could stick around after class if you had questions, but you can also put them up on the discussion board, and then
Okay.
I'll actually cover them in class.
Okay. Okay.
Yeah.
Sounds good.
All right.
All right. Thank you.
You're welcome. Hold on, Kara. I'm going to put it into the chat right now. All right, I'll see you over there in just a second, Kara. So if you just copy and paste the link, and then because I think you have to leave this meeting. See you, Ravi.